T-distributions can be used to find the significance test for some numbers. So we can come up with some number and then look into its probability of finding under a t-curve. So for instance, we can have a one sample t-test where we are having some claims or some standards and against which we are testing some samples. So for instance, you have some claim that the fuel efficiency of some car which is given by the company is say like 15 kilometers per liter, but you want to doubt in it and you want to test its statistical significance. So over here you can run some cars, you can take a sample of say 10 cars, calculate their average mileage, and then you can test against their claim. Another example is in case of gene expression studies. For instance, you are given some number like there is some expression number that is given as 10 rpkm, so you want to doubt whether the actual expression is greater than that or less than that. So let's take this gene expression example. So here we are interested in expression of this TP53 gene family. So that TP53 encodes a protein called as P53, which is a tumor suppressor gene. We believe that this expression is greater than 10 rpkm. We sample 11 genes, say they are belonging to TP53 gene family, and we found that the mean expression was 12.35 rpkm. Whereas the standard deviation for this distribution, these 11 numbers, they comprise of a distribution. So that is this standard deviation is 1.5. Since n is equal to 11, our sample size 11 genes, y bar or the sample mean is 12.35, and s, which is the sample standard deviation, is 1.5. Here we introduce another number, that is our value, which we call it as standard error of the mean, or sy bar. So that is given by standard deviation divided by square root of n, which is 1.5 divided by square root of 10, which is 0.475. The calculation for t is given as y bar minus mu naught divided by sy bar. We call it as t calculated. That is the t calculated for this given sample mean. Here is 12.33. When we plug into that equation, we come up with the t calculated as 4.91. So this, on a t scale, the number we get is 4.91 for this sample mean, which was actually 12.35. Now we draw the null distribution and we look into whether this number is, this t calculated is a significant number or it is present in extreme tail values. In that case, it will be significant. So if we plug in these in Excel, we have the formula in order to calculate the critical values. Here, when we are doing the hypothesis test, we do these tests on your null curve. So here, this is the curve under the null. So under the null hypothesis, it is true. If the null hypothesis is true, so here the mean is at 0, and we can have the t calculated at different intervals. So for instance, if we want to go at top 5%, we can plug in Excel. There is a formula called as t dot inverse, where we put in 0.95, that is the probability up to that point. So under the curve, the probability area under the curve is 1. So we start from 0 towards the left and then we go up till towards the right. So here the total area is 1. What is the 95% of the area? So it's right here. So what is the p value at that point? That is equal to 1.8, which we calculated from here. So in terms of probability scale, it's 0.95. So all these red shaded area indicate that 95% values are up to that point or below that point. Where are upper 5%? Obviously towards your right, this green area. So if our observation or if our calculated t is greater than this 1.8, our results are significant. In that case, we can say the probability of finding this thing is greater than 0.95. So it's present, the observation is present in upper 5%. While if we start looking it towards the right hand side from this side here, so in that case this probability should be towards this right. If you are looking from this side, so it should be less than 0.05. So we plug in those numbers. The T calculated is 4.9, whereas T critical over here was 1.8. So anything beyond that, any T value greater than that is a significant event, so which is 4.91. So obviously our difference is significant. So the mean expression is actually greater than this given mean, which was the given number, that was the number was 10 rpkm, which lies somewhere here. The probability of this T calculated in terms of probability scale, so that is 0.999604. And if you look towards the right, this blue circle indicates that this probability is actually 0.000306, which is less than 5 if you look towards this side. So it's far less than 5, so this is a significant event. We can interpret this p-value as having seen this event, so that is 0.0003, that is 3 out of 10,000. So probability of seeing this event by chance is 3 out of 10,000. It's very, very low, so it's a significant event. We can calculate the differences, what the difference should be greater than some number. So if the given number was 10, where our T critical should have been 0, or where our probability was 50% or 0.5. So if we want to correspond it with the actual number, so the difference, any difference greater than 10.86 will lie somewhere here. So that is a significant difference. So in case of the RNA-seq data, t-tests are not preferred because t-tests assume the normal distribution. So for microarray it's fine, but as far as the RNA-seq data is concerned, since we are taking the reads and we are aligning them onto the genes, so there are two possibilities that those reads will align those reads, will align on those genes, or they will not align on those genes. So in that case, it's kind of a binomial problem. So these tests like t-test, which assume normal distribution, they do not fit into that situation. So rather than that, we have to use binomial tests, which are implemented in AGR and DE-seq. So how can we conclude our results as on the basis of the p-values? So p-values are, we are given some threshold or standard. So we have the curve and we declare anything significant if it is present in top 5%. So in that case, their probability should be less than 0.05. So less than 0.05 means that they should be present in upper 5%. So here our calculated p-value, again we are looking at from the right hand side. Remember guys, it's hard to assimilate the concept of hypothesis testing using p-values, but here if you are using the p-values, you have to compare them with your significance level, or alpha. We call it as alpha or error also. Why we call it as error? Because under the curve 5% of the values should have been there, they must have been there. So under normal circumstances, and there should be 5% of the values present in that tail. So you may be wrong 5% of the time. So in that case, we call it as error or alpha or type 1 error. We'll discuss them later on. So we conclude that this TP53 gene family, the expression of this gene family is greater than 10 rpkm, and probability of the expression greater than 10 is 0.0003, which is actually 3 out of 10,000. So it's a very, very rare event. So probability of finding this thing by chance is 3 out of 10,000.